Hey everybody, this is Morgan coming back at you. We're still talking about bonding. We're going to do pages 8, 9, and 10 of this outline today. Now this is a very interactive lecture typically. So what I'm going to start off with is telling you to go watch the video that I've put up in the Schoology group for Honors Chem that I just called Milk Bottle. Okay, go watch that one, pause this, and you can come on back. Okay, now that you're back, we need to distinguish between intramolecular and intermolecular forces. Intramolecular forces are bonds. Any type, covalent, ionic, you get the idea. Now, intermolecular forces are not bonds. They are attractive forces between two separate molecules. Now, those molecules can be the same or they can be different. And it is also possible that this could happen just between atoms also. Okay? So bonds are, maybe we would say, permanent, and the intermolecular forces less so. Okay? Bonds are definitely stronger than attractive forces, but attractive forces can be strong also. Okay? Just not as strong as covalent bonds. All right. There are three types of intermolecular forces. The first is called the London dispersion force, and this is a temporarily induced dipole. And there'll be a video for you to go and watch right now about that. Okay, temporarily induced dipoles happen when you have two species. We'll just make it two atoms this time that are side by side. Could be molecules. And for some reason, electron density gets heavy on one side, weak on the other. So the atom next door will also have the same thing happen. These are dipole moments, like we talked about in our last lecture, except they're temporary. We cause them to happen, okay? So they're not going to be as strong. All species have these, all species. Okay? There are always London dispersion forces present. But sometimes they're so weak that we really don't talk about them very much because we'll be talking about dipole-dipole or hydrogen bonding instead. Okay? Now, we can cause these dipole moments to form by putting a positive charge somewhere or putting a negative charge somewhere, okay, and causing atoms to have their electron clouds become polarized. So they're polarized electron clouds. But as you know, electrons are moving, so that disappears pretty quickly. Now, dipole-dipole forces were our last lecture. They are permanent, E-N-T, permanent dipole moments. Okay? And hydrogen bonding is a terrible name. Okay? Because it's not a bond. Even though it has bond in the name, it's not a bond. So it is an especially strong dipole-dipole force. Between hydrogen and one of three elements: nitrogen, oxygen, or fluorine. Now, why only those three? Well, they're all very electronegative. There are other elements that are just as electronegative also, but they don't do it. It's that they're all very electronegative and they're relatively small atoms, so that they can get close to a hydrogen. Okay? Size. This is Coulomb's law again, folks. Size has everything to do with it. Now, we know these exist in water. You talked about them in biology. And they can exist in things like methanol that have an OH group in them. Okay? But one thing to note, the hydrogen must be directly bonded to the nitrogen or the oxygen or the fluorine for this to work. If you have something like this, carbon, double bond oxygen with some lone pairs, carbon and carbon, no hydrogen bonding would exist in this molecule. None. Because the oxygen is not directly bonded to the carbon itself. And that's a really important thing. Okay? So, let's start applying some of these ideas here. What's going to determine a substance's boiling or melting points? Well, IMFs, the intermolecular forces. Don't say molar mass. Common misconception. The stronger the IMFs, the higher the melting point or the boiling point. Now, in something like a salt, like sodium chloride, NaCl, the IMF is actually an ionic bond. So it has a very, very high melting point. You watched a Julia Child video about this last week. Okay? Now, in something like helium, which only has London dispersion forces, okay, that's a very weak attraction, so helium exists as a gas at room temperature. And in fact, it's a gas all the way down to something like 4 degrees Kelvin. Okay? Now, hydrogen bonding can cause really interesting things to happen in water. So this is going to be the water video. Watch that. See, when water goes from the liquid to the solid phase, the molecules all line up really neatly and orderly. And the spaces between the molecules get bigger. The molecules don't get bigger, but the spaces between them do. And what that means is the volume of a sample of water, when it freezes, becomes kind of larger. And you probably realize this already by exploding a Coke in the freezer. You can't put a closed can of Coke or a closed bottle of Coke inside the freezer because it's going to expand, it's going to break the bottle. Okay? So, what that really means to us is ice cubes float. Ice cubes float in water. Solid water is less dense than liquid water. Okay? Go check out the videos about that. Now, IMFs are also what hold DNA together. Okay? Hydrogen bonding. And since it's not permanent, it can be broken, and that's why DNA can replicate. All right. Now, van der Waals forces. That's just an old name. I want to add it into this lecture only because I know it still exists in the AP Biology book, for those of you that are taking AP Biology. Van der Waals forces is a name for London dispersion forces and dipole-dipole forces together. Okay? It's just kind of a blanket name. Before we actually knew what these were, we called them van der Waals forces, not hydrogen bonding. I will not ask you any questions about van der Waals forces. I will use the proper names of LDFs and dipole-dipoles, but the biology book uses that term. Okay. You might be familiar even with an idea called capillary action. So we're going to have a video here also. Okay, and you will be able to go in and see how liquids can rise up inside of very narrow containers. And what that means is a tree can actually drink. Water can get to the leaves up at the top of the tree, okay, by water being carried up narrow tubes. Okay. Now, differences in strength for these forces. Ammonia is NH3. It's a gas at room temperature. Water, H2O, is a liquid. Gas, liquid. Water has two lone pairs on the oxygen, and ammonia only has one, meaning more hydrogen bonding can exist in water than in ammonia. And that's why water will be a liquid at room temperature, but ammonia gas will actually, well, ammonia will be a gas actually. Okay. Boiling points for helium versus xenon. Helium lower, xenon higher because of LDFs. Xenon has more electrons. Therefore, it has what we call a more polarizable electron cloud. And that means more LDFs, stronger LDFs, and xenon would have that higher boiling point. Okay, now, going on to our last page here, we're going to look at some different species and identify what the IMFs are. But the term interparticle forces may come up at times. When I say IMF, the M implies molecule. But sometimes they're just atoms. Sometimes they're ions. Okay? So we're starting to change the name now over to calling them interparticle forces rather than intermolecular forces. Don't freak out about that. That's fine. So, interparticle forces are what determine melting points and boiling points. The stronger those forces, the higher the melting point of the boiling point. Now, every substance that we know of has LDFs. They exist in everything. But the only ones that have dipole-dipole forces are those that have dipole moments, like NaCl, KCl, NH3, H2O, and even HF. But there are even stronger forces present in NaCl, KCl that are ionic bonding. So we tend not to talk about these very much. Now, ammonia, water, and HF will also have hydrogen bonding. To have hydrogen bonding, you must have a dipole-dipole. And everything has got London dispersion forces. Okay, that's the last few pages of the bonding outline. A lot of videos to watch for this one. This would have been pretty much a demo-based lecture for you folks. Okay, have a good day. This is Morgan signing off.